Have you ever stopped to think about the invisible energy that's, well, literally all around us? It's not just random, it's actually governed by this invisible landscape, a kind of map of potential energy. And today, we're going to learn how to read that map. So, let's kick things off with a real mind bender. How in the world do you store energy in what looks like totally empty space? I mean, really think about it. The answer, as you might guess, isn't in what we can see. It's all about the invisible forces and fields that are filling that space. Okay, to wrap our heads around this, let's start with something we all get: gravity, right? It acts on mass. Well, the electrostatic force is kind of like its cousin. It just acts on charge instead. But here's the crucial part, the thing they have in common that changes everything. They are both what we call conservative forces. And trust me, that one little phrase is the key to this entire story. So, because that Coulomb force is conservative, it means we can think about storing energy in an electric field in the exact same way we think about potential energy from gravity. You know, like a bowling ball held at the top of a really steep hill. It's the same fundamental idea. But what does conservative actually mean? It's a fancy word for a really simple but powerful idea. Imagine you need to move a charge from point A to point B. A conservative force means that the amount of work you have to do is exactly the same no matter what path you take. You could go in a straight line, you could zigzag all over the place, you could do a giant, ridiculous loop-the-loop. It doesn't matter. The energy change is identical. And this path independence, that's the only reason the whole concept of stored potential energy even works. And this quote just nails it. Think about it. If the path did matter, then a single spot in space wouldn't have a single specific energy value. You couldn't say the potential energy right here is X joules, because the answer would be, well, depends on how you got here. The fact that the path doesn't matter is what makes the whole idea of potential energy make sense at all. So this powerful idea lets us define a property of space itself. And the best way to think about it is as an electrical version of height. Right? The higher up you lift a book in a gravitational field, the more potential energy it has. It's the exact same principle for charges in an electric field. Okay, now we got to be really clear about something, a super important distinction. There's potential energy, let's call it U. That's something a specific charge has when it's sitting at a location. But then there's something more fundamental, and that's the electrostatic potential, which we call V. This is a property of the location itself, whether there's a charge there or not. It's the potential for energy. It's like the height of the electrical hill, just waiting for a charge to come along and have some potential energy. All right, so if we're going to get formal for a second, the official definition of electrostatic potential, V, is the work it would take per unit of charge to drag a tiny positive test charge all the way from infinity, from super far away to one specific spot. You can almost think of it as a measure of the electrical pressure at that point in space, which is created by all the other charges around it. And this visual, man, it just makes it so clear. Look at how the potential, our electrical height, sort of gently fades away as you get further from the charge. But the electric field, that's the steepness of the hill, the actual force. And that drops off way faster. It's a much more dramatic fall off. Okay, so now that we have this awesome analogy of potential being electrical height, we can actually start to draw maps of these invisible energy fields. It's just like a cartographer mapping out mountains and valleys on Earth. So let's check out our first map. If you've just got one single positive charge, the landscape is basically a perfect hill. And these circles you see, those are called equipotential surfaces. Equipotential, equal potential. It just means that every single point on one of those circles is at the exact same electrical height. They're literally contour lines on an electrical topographic map. But what happens when we start adding more charges? Well, this is where the landscape gets really interesting, really complex and beautiful. You put a positive and a negative charge near each other. That's called a dipole. And you get this amazing hill right next to a deep valley. Or put two positive charges together, and you get two hills with this sort of saddle in between them. By drawing these maps, we can literally see the energy landscape of the space. And all these maps, no matter how complicated they look, follow a few simple rules. First, by definition, staying on one of those contour lines means you're at a constant height, so it takes zero work to move a charge along it. Second, the electric field, the actual force, is always pointing perpendicular to these lines. It's always pointing in the direction of the steepest downhill path. And just like water flowing down a hill, that field always points from high potential to low potential. Simple as that. Okay,
This is all really cool, right? Mapping invisible landscapes. But you're probably asking, so what? What's the real-world application here? Well, this whole concept of electrical height, or more accurately, a difference in potential, is the absolute key to one of the most basic and important electronic components ever, the capacitor. This is how we actually store energy in an electric field. And you know what? At its core, a capacitor is just ridiculously simple. It's nothing more than two conductors held at different electrical heights, or potentials, with an insulator separating them. Just picture one metal plate sitting on a high plateau and another one down on a valley, with a little air gap in between. That difference in height, that potential difference, that's where all the magic happens.
So how does it actually store energy? Well, you hook it up to a battery. The battery is basically a charge pump. It starts pushing positive charge onto one plate and at the same time, pulling it off the other plate, which makes it negative. This separation of charge creates a really strong, uniform electric field in the gap between them. And on our energy map, that looks like a perfectly steep, even slope. And that field, right there in the gap, that is the stored energy. And the way we measure how good a capacitor is at doing this is with a value called, you guessed it, capacitance. It's just a ratio, C equals Q over V. It tells you how much charge, Q, you can pack onto the plates for every 1 volt of potential difference, V, that you apply. So a capacitor with a high capacitance is awesome because it can store a ton of charge without you needing a crazy high electrical height difference between the plates. It's a super efficient way to store energy. But wait, to really get how capacitors work and to understand potential in the real world, we need to talk about one last crucial piece of the puzzle, and that's the special properties of the materials we build these things out of, conductors. See, conductors have this really fascinating property. The charges inside them are free to move around. So if you stick a conductor in an electric field, those little charges immediately shuffle around until they completely cancel out any electric field inside the conductor itself. And what's the result? The electric field inside a conductor in a static situation is always 0. And if the steepness is 0, what does that mean for the height? It means it's perfectly flat. The potential is constant everywhere inside and on the surface. And this leads to a pretty incredible phenomenon called electrostatic shielding. If you take a conductor and you hollow it out, the charges on the outside surface will arrange themselves perfectly to make sure the electric field inside that empty cavity is always 0. I mean, always. It doesn't matter what kind of crazy electric fields are raging on outside, the inside is completely shielded, completely protected. And this brings us to the classic real-world example everyone talks about. You know why you're safe inside a car during a lightning storm? It's not the rubber tires. Nope. It's because the metal body of your car is a conductor, and it acts as an electrostatic shield, a Faraday cage. If lightning strikes, all that massive charge flows harmlessly over the outside surface, while the electric field inside the car stays at 0. It keeps you perfectly safe. So, there you have it. We've gone from a simple question about storing energy in empty space to mapping these incredible, invisible landscapes of electrostatic potential. We've seen how understanding this electrical height lets us build devices to store energy and even shield ourselves from one of nature's most powerful forces. It really makes you wonder, doesn't it? If this one invisible field shapes so much of our world, what other unseen landscapes are still out there just waiting for us to figure out how to draw the map?